There we go, I started recording. So yeah, we'll pick up from where we were last time. So when, nope, I went the wrong way. Okay, so this was the question I wanted to start with again here. How would our implementation need to change if we had the top be 0? So the way we're thinking of it now is if we had an array. I'm going to draw it like this. Right? And I had things in here. Like the top always grows from this end. Not at like the index 0 end, but it grows at the other end. But this question's asking, well, what would we need to do differently if we wanted the top to be 0, always 0? And I guess a benefit of that would be we don't need to have like a variable holding on to where the top is or anything. But let's think about what this would mean. If we want the top to always be 0, drawing my funny looking array, looks more like a fish or something. And if this is index 0, and I had like this many things here, if I wanted to add something new, if I wanted to push something onto this stack, what do I have to do? Well, I'm going to have to move all these things down to make room for the new thing. And similarly, if I wanted to remove something, and we take this X out, we're going to have to move everything back. Which is a little bit problematic, because when you think about over here, and you'll see that this is a very common theme in this course when we talk about like computational efficiency. Whenever we add something here, it's like it's one set of steps. It's very simple. The amount of work we have to do does not matter, or pardon me, the amount of things in our stack doesn't really impact too much how much work we have to do here. I mean, we've got expand capacity, so there's an asterisk there, and expand capacity takes time. We got to copy everything over. But if I wanted to add something new, I just put it here and increase top. That's it. Where here, in this case, if I'm doing all these shuffling around, if I have n things in my stack, I'm going to have to shuffle n things every time I push, and then n things again every time I pop. So where this takes a constant amount of time, this example of having it start at 0 will take more and more time to push and pop things the bigger our stack gets. So this would actually be a really terrible idea. We wouldn't want to do it this way. So yeah, what do? We defined a stack. We use the definition of stack to solve a problem. The really bad example of postfix. We implemented a specific stack, the ArrayIntStack. But the one really big thing here I want to make sure I'm emphasizing is that, again, the definition and implementation of this data structure, of this stack, they're independent. What you can do with the stack, the push, pop, peek, doesn't tell you anything about how it does what it does. We wrote the implementation for our ArrayIntStack. So we actually, we did say how push works, how pop works. I know that. But the point here is that these things are ultimately independent. And if it's not obvious yet, it will become more obvious once we look at another alternative implementation of a stack, just with something that's not an array. Okay, so there we go. Are there any last questions about stacks before we go on to our nodes and links? Let's go have a look. Anything? Okay, well, I guess not. All right, so let's go on with nodes and links. All right, so the point of this lecture is we're going to see a different type of container, kind of. And I'm using the word container to be like, well, an array, that's where we put some information, right? And we used an array to build a stack. Instead of just arrays, we're going to implement nodes. And we're going to implement a series of nodes as well. And they'll be linked together through pointers. And we'll see how we can add and remove things from these interesting linked structures. So, what I'm about to show you is not a new abstract data type. this does not fall into like the stacks and the queues that we're going to see and the trees that we're going to see. This is a thing that we can use to build them, but this is not actually a new data type or an abstract data type that we're defining. We're just prepping to be able to start implementing these things with stuff other than arrays. So what are the limitations of the arrays we've been using? Well, I mean, they have a fixed size, but we can expand capacity. So that's not too bad, but it is a little bit more work, I suppose. And adding and removing things may require a lot of shuffling around. If I remove something from the middle of an array and the order matters, I might have to shuffle a lot of things around. That could be painful. That could take a lot of work. And the array also must be in like a contiguous chunk of RAM where, I mean, this isn't really going to be a problem on your computers, right? But if you imagine I'm programming on an old or a small computer with very limited amount of RAM, that might end up being problematic if I've got a large amount of data. So we're going to use these things called linked structures, and they're going to consist of things that are linked together with pointers. And we can use this idea to implement a lot of other crazy abstract data types. But we're going to focus on singly linked structures here. I will say that with what I'm about to teach you, you will find a lot of other people, a lot of textbooks that don't call these things linked structures. I call them linked structures for very good reason. The reason is because other people will call them linked lists. But linked lists actually means something else. So the word linked list has started to play double duty, and that double duty, the two different things that that is used to mean are very similar. So that it leads to a lot of confusion, year after year after year, such that I was like, no, they're linked structures. From now on, that's what I'm calling them, because they are linked structures. And then we will use these linked structures to build linked lists later. So here's the idea. I'm going to have some variable that's a pointer. Let's say I call it head. This is a typical variable name for it. So this right here, this is just a pointer variable. Okay, so it's just a variable with a pointer. So a memory address to the first node. This is a node. This is a node. This is a node. And so on. Okay? And these right here, the little blue arrows in between, are also pointers. But this pointer will be one of the attributes of a node object. So, oh yeah, nodes, a pointer to, look at that, I already had it. Hey, look at that. So linked structures advantages. Well, we can have a lot of data stored consecutively, but not in consecutive RAM. And we can actually insert and remove things without having to shift everything around in interesting ways, and we'll see this. And they do not have a fixed size. They can just keep growing towards infinity. So how are we going to do this? Oh, yeah, I hear something. What's up?
So in that slide where you had all the nodes and the pointers, those are just single pointers and not like pointers or whatever?
Yeah, these are just, I mean, you're looking for implementation details at this point, where this is more an abstract level stuff. So we will go into those details in a moment. But at this point, yeah, this is just a pointer to a node. It'll be like a node pointer, and we haven't defined a node yet. But again, that's the implementation issues. Okay, so how are we going to do it? So we'll see actually how remarkably simple it is to make a node, and then use these nodes to make linked structures. So we need a node, and a node is going to be the basic unit. A node will be analogous to one of the indices of your array, okay? It's just one little unit of a linked structure. And it's just, the linked structure is going to be a sequence of these nodes that point to their successors. And a node in a singly linked structure typically has only two attributes. I mean, we could put as many as we want, but typically you're going to have two attributes. The data that it holds, and then, like, to compare it to an array, this would be the stuff we're putting in a specific cell, in a specific index of the array. And a pointer, a link, to the next node. So if I had an array of like 1, 2, 3, 4, this is the data in it. 1, and then the 2, and then the 3, and the 4, and the 5. If I were to have like a linked structure like this, I would have like 1, 2, 3, I don't know, 4, 5. And I guess we'll have our pointer to the head as well. So this is the idea. The one, that's like the same thing that we're putting in the array, and the arrows, the pointers, they're telling us where the next one is. Yeah, arrays don't have this because they're just already in contiguous RAM. Right. So with an array, I know exactly where to find the number that comes after the 1 in this example because it's going to be in the next available RAM spot. There's no magic to it. It's just, okay, where do I have to go look to find another integer? Where in this example, there's no assumption that these are in contiguous chunks of RAM. In fact, they very likely won't be. So we need a pointer to where that thing is stored in RAM. So here's an idealized drawing of a link structure. Again, similar to the first one, but I've kind of drawn the nodes out here to be a little bit different, where it shows like, well, data and pointer, data and pointer, data and, well, here this is a pointer to null. So this is like a null. The end has a pointer to nothing. Look at that. I've beat myself to the punch this whole time. So here's what we're gonna do. Our node header. We're gonna have I'm gonna make an integer node. It's gonna have an integer pointer. That's gonna be the data. And then we're gonna have an int node pointer, a pointer to something of itself, of the same type. We'll have our constructors, and then we'll have our get data, set data, get next, set next. That's it. Basically getters and setters for these two attributes. That's it. That's the whole header. So here's what I'm going to do. I know this was the same project where we did the course and the students, but that doesn't matter. I'm going to add a new class. Nope. Int node. There. So I've got my header, int node. It's going to have an integer pointer. That's going to be the data. That's the information we're storing. And then int node pointer. That's the next. Got our constructors and got these things. That's it. That's it. It's simple. 2 attributes, the constructors that we typically write, and then getters and setters. That's it. Why wouldn't you also want a pointer to the node before? Well, you could totally do that, but that's called a doubly linked structure. And we won't do it because it's slightly more complex, but periodically throughout this course, we will high-level talk about them. I mean, they follow the exact same principle as the singly linked lists, but there are added complexities, but also added benefits of it. And in fact, I think if I go to the very last slide, haha, look at that. Look at that. You beat me to it too. So this is an example of a doubly linked one. Anyways, spoilers. Where the heck? Okay. All right. So here's a question for you. How do we access the first item's data? Okay, so when we think of like head, imagine head is in our main. And then we have like head, we have the variable head that is, it's a pointer to the first node, the head node. How do I get this data? Does anyone have any ideas? Type it in based on what we saw here. I have head. That's a pointer to this node. What do we have? Use the right pointer type to access the thing you want. Yes, you're right. I mean, I guess I won't be picky and make you go more specific, but you would have head, which is going to be a pointer to a node. It would have to be in this context. And I would write something like get data. right? Why? Well, because the get next is to get, well, maybe you answered this question. How would I get this one? Well, I would have to say head get next, which returns a pointer to the next one, get data. And how would I get the third one? Well, head get next data. And so on and so on. But here's the trick question, and this actually goes to what you were asking a moment ago. How do I get a node's predecessor? I mean, I can get its successor by saying next, or get next. But how on earth am I going to get, like if I have, let's say I have a pointer to this node, right? Somehow I just have a pointer here. I'm gonna pick a different color because it can get confusing. There. I have a pointer to this node. But I want to access this one. How the heck do I get this? Does anyone have any thoughts on this? It's address. Well, ultimately correct, but I'm looking for something a little bit more specific. I need to get that memory address. How do I get that memory address from here? Do one less get correct, but imagine I have some arbitrarily long list, okay, where it's like, I don't know, the head, then I have and then some last node pointing to null. And I happen to have a pointer to this memory address. Who cares how I got there? The way, I mean, I would have got there probably through like accessing the head and calling get next a bunch of times, and now I have a pointer here. But I'm currently here, I'm here. How do I get that one? And I mean, you're absolutely right. You would do one less get next than you did the first time. But see, the problem here is I don't have a pointer that gets me to the previous. If I had what Cole was just asking about with the doubly linked list, where I've got a pointer, pardon me, to the successor and predecessor, this would be easy. I could be like get predecessor, get before, whatever I call it, and then it would, you know, just return this memory address. But I don't have that. This is not an option. So, I mean, if I called get next 100 times, well, I could just go ahead and call it 99 times, and there, I've got it. But also, maybe I'm in a situation where I actually don't know how many times I called get next. How could I do this? How could I get this one? Look at the address where the data is stored and find the RAM with that address. Well, yeah, but that's what we need. Like, we don't have the address. The question is, I don't actually know where this is in RAM. Like, I only have a pointer to here, and I have a pointer to the head. And there is some node in here that also has a pointer to this guy, right? But from this pointer, I can't easily just know what memory address this is. So how the heck do I get there? Let's have one more guess before I spoil all the fun. Someone's got to have some idea. It's gonna get super awkward if someone just put in a guess. What do we got? Start from the head and from other nodes you have. And from, well, yeah, okay, we start from the head. Okay, that's a good start, but then what? What do I do after I go to the head? Okay, from the head, then what? Increment up. But yeah, but until when? Like, well, increment. I'm assuming you mean like keep calling get next. Is that what you mean? Yeah. Yeah, sure. Okay, but I mean, how do I know when to stop? How do I know when to stop at the predecessor? Start from the head and keep track of how many get next you used. Yeah, but let's say I don't know, like, too bad. I don't, wait. Oh, okay. So you know what, Cole, I'm going to take your idea and modify it slightly. So what you said is start from the head and call get next however many times you need to get to the node I'm pointing at. And then I've kept track, I've counted. So then I can just do a loop again with x minus 1 get nexts, and then suddenly I have the predecessor. That's what you mean, right? So what about this? What about this? What if I have something like while, I open up paint because I'm running out of room. Nope. While, so we could do something like, okay, cur equals head. Okay. And then we can be like, well, cur dot get, or I guess arrow, next is not equal to, I don't know, that other node. There. Do cur equals cur get next. That's, trust me when I say that says next. So there's the idea. Well, the current's next is not the node that I have access to. So that's like, I have the node, I've got this node, I've got this one, I want this one. Start from the head and keep asking the question. Like, I'll draw one more node before it. Hey, current, this is cur. In one snapshot of this loop iterating. This cur, what's your next? Oh, well, it's this one. And I ask the question, is it equal to the, like, that other node? This is other node in this case. And if it is, or if it's not, like, move cur down. Okay, so cur is now that one. And then I ask, is cur's next the other node? And then in this case, it'll be like, yeah, it is. Well, then I would stop because now I know cur is the one before. So that's a slight modification on what you were saying. So we know the data in the final one? No. No, this is just I mean, well, this has nothing to do with data at this point too. This is just pointers to node objects in RAM. I mean, all of these things have data in it, but that doesn't really matter right now. So we know the data in the final. No, I'm not sure what you mean. Maybe this is just assuming the node data when you say that's not get next is a pointer to a node, not the data. You would need get data. So we know the data in the final one. I still don't understand the question. If I'm at an sorry, yeah.
That while loop where you
Yeah.
have it does not equal to other node.
Yeah.
So we know what other node is, like we know what we're not equaling.
That's, in this example, it's we have a pointer to some node in our linked structure. Somewhere. I don't care where, it's just in general, somewhere. There are edge cases like, well, what if it's the first node and what if it's the last node? But it's some node somewhere in this linked structure, and I happen to have a pointer to it. How I got there, don't worry about it. That doesn't matter for this question. I have a pointer to a node. I want to get the node that comes before it. How do I do it? That's all. That's all I meant. Yeah, and how is this different from arrays? Well, we have to use get next. And with an array, I mean, you know where the next is because it's in the exact, like it's in the contiguous place of RAM down the line in RAM. And we also know the previous though with an array. With an array, we can easily go both ways. We can jump all over the place in an array. Or with these link structures, we need to like keep doing like next. So you win some, you lose some. how do we add something to this like linked structure here, this lists? And I suppose there are like 3 versions of this question. How do we add something to the front? How do we add something in the middle? And how do we add something to the end? And I mean, maybe they're not even 3 separate questions, but maybe they are kind of 3 separate questions. Maybe there's some special rules. And similarly, how are we going to remove something? How are we going to remove something from the front, the middle, and the end? How do we do this? Well, when we add to the front, this is perhaps a really easy, an easy one. I have a new node. It's pointed to by a variable called node. Okay, so this variable here, it's a pointer to some node somewhere. And I have a pointer to the head of my linked structure, which is this yellow one. How do I get it such that head is pointing to the blue one, and then the blue one points to the yellow one, then the yellow to the gray, and the gray to the black? How do I do this? Well, node points to, yeah, I just said that. Well, here's what we do. First, and the order here really matters. First, say, okay, node, your next is going to be set to head. Okay? Or to be more precise, you're going to be pointing to what head points to. And then say head, well, you're now equal to node. Boom, done. That's it. That's it. But we got to be careful. Imagine for a second we did the opposite, where I had like node pointed to this thing, and then head, which was pointing here. Right? So first I said, okay, node, your next is now this, and head, you now equal node. Okay, that's the correct way. But imagine I said, okay, head equal node. Oh, okay, so this disappears. There we go. So head is now this node, which is correct, but how the hell am I going to now set heads next to be, like in this case, the yellow one? I can't. I have now lost, I've lost my pointer to the beginning of this link structure. Imagine this list had 1 billion things in it. And the only way I can get to any of those billion things is through the head. If I lose access, if I lose track of where the head is, I've just lost everything. So we got to be careful about the order, because if we did it in the reverse order, we'd be in big trouble. And this idea of the ordering really mattering here is going to come up with all these add and deletes. So adding to the middle. Well, I've got some node, and I've got some linked structure here with a head pointer to the first node. How am I going to add this to the middle? Let's insert the new one in the third node, after the third node. So I guess between this, I don't know, cyan and black one. Insert there, okay. How am I gonna do this? Well, take a second and think about it, because it's actually not gonna be too bad. First, we're going to need to find the node that is to come before the blue one, the one we want to insert. So we need to get a pointer to, in this case, the cyan one. And then once we have that, and again, here's where order is really going to matter. We're going to want to put the new nodes next to be the same as the currents next, then make the currents next be the blue one, the one we're inserting. And now we've got it. This is it. We've got, look, we go head to this one, head to here, to here, to here, to here, to here. Great. We've now inserted it between the two. And you'll notice that, like, again, imagine if this list was 1 billion things long, right? If this was an array, and I wanted to insert something into an array of a size 1 billion in the middle, I'd have to shuffle a lot of stuff over. But here, I didn't have to shuffle anything down an array, right? I was able to just kind of like insert it right into the middle, no problem, by just updating what the pointers were pointing at. So this is wonderful. This is a huge benefit of these link structures. We don't need, like, imagine I added something to the beginning. Even adding something to the beginning here, right? In this case, if I had an array of size 1 billion and I wanted to insert something into index 0, I'm gonna have to move a billion things. Move the billionth thing to a billion and one. Move the 999,999,999th thing to location 1 billion, and so on and so on and so on. Where here, it's just like one, okay, what is it? We got the node. It's 1 step, 2 steps, done. That's a heck of a lot better than a loop that's gonna run a billion times. So this is a huge win. But again, imagine for a second that I didn't do this step first. I said, oh, okay, current, your next is now the new node. And then this pointer is gone. Well, now what points to the black node? Well, currently nothing, and we've just lost this node and everything that comes after it. So we're in big trouble. So again, order, super important here. And adding to the end, well, so we saw that adding to the front was kind of a special case. It was easier than adding to the middle. But adding to the end isn't actually really a special case. It's the exact same thing as here. So imagine in this case, this is pointing to null pointer, okay? And I wanted to add something here at the end. Well, I would still have to get access to here somehow, cur, and then say, okay, node, your next is going to be equal to current's next, which will be a pointer to null. And then cur, your next is now going to be the new node. There. It's actually the exact same algorithm, whether it's inserting in the middle or at the end. It's only the adding at the front that's kind of the special case here. And then deleting from the front, this is actually really easy. Head points to the first node. All right, just do that. Done. Problem solved. But, do I have it? No. But what am I going to have to make sure I do here? Does anyone have any idea? Assuming all these things, here's a big hint. Assuming all these things are in dynamic memory, what am I going to have to make sure to do? Someone type in the chat. I know someone in here is going to know. Delete, of course. It wasn't an overly tricky question. And actually here, I have to be careful. If I don't have a pointer, something called like toDel, and then I update head, if I don't have a pointer pointed to the original head, I'm going to completely lose access to the original head, and without a pointer to it, I won't be able to delete it. I'll be in big trouble. So I'm gonna have to make sure I make a pointer to the thing I'm gonna want to delete, assuming I want to delete it. And then after I update head, well, then I can delete to delete. Deleting from the middle. Okay, so let's say current. This is the one I want to delete, let's say, and I've got previous. So somehow I've got these 2 pointers. And you could actually do this with 1 pointer, like just previous, but here's what we're gonna do. Just say, what? Is this the exact? Okay, it's the same. Whoop, I hear something. Would you need to keep track of the last node's pointer if it's always? Yes. So okay, I suppose we don't really need to, but you're definitely going to want to need to, because if it's not null pointer, whatever value is stored in that pointer that is at the end will be a valid memory address. So if it's not really pointing to something meaningful, how am I to know? Here's what I mean. How am I to know if that last node, if it's pointing to something meaningful or not? And the way we do that is by having the last node point to null pointer. Because if it points to null pointer, I know that it's pointing to nothing, and I know that I must be at the end. Otherwise, I might just assume that, oh, I should go to this next memory address, whatever garbage is in the pointer variable next for that last node. Where does it tell me to go? And it'll go, and it'll be garbage there. It's not going to be very useful. It's going to cause a lot of problems. So null pointer is used to signify that, like, okay, you're a pointer, but you point to nothing. And so this is actually an easy way to tell if you're at the last node. Imagine I have a loop that's like, okay, cur equals cur get next, okay? So I keep iterating down. But I can always ask if it's the end. If cur's next is null pointer, now I know cur is actually pointing to the last node. I think I'll have an example of that in a slide or two. So here's what I want to do. I need to, I feel like I'm missing, okay, no, here we go. So here's what we're gonna do. I will say previous, your next is what current's next is. And then I'm gonna wanna delete current after, assuming I want this actually deleted and I'm not using it somewhere else in the code. So this is how you would do it. Alternatively, if you didn't have this current pointer, you could just say previous, your next is equal to your next because it's next. I guess I should use a different color because you can't see. Because it's next is the black node in this case. So you don't need the current, but when you do have the pointer to current, it makes it easier to delete here anyways. Otherwise, if we don't have any pointer, we're in trouble. Yeah. And deleting from the end? Well, is deleting from the end a special case? Well, let's think about it. What's this one point to? If this is cur, this is previous. I guess if I just set this one's next to this one's next, this is like null pointer, it'll just do that. So I guess it's exactly the same. So deleting from the middle and the end is also the same. It's only deleting from the beginning that's a little bit different, is the edge case. Okay, so I have told you what we can do with this node, but we didn't talk about the implementation. Well, let's talk about the implementation. This is what we want. I'm going to make an integer node, and I'm going to have two attributes, data and next. The data attribute is going to be a pointer to some integer, and next is going to be a pointer to some node. Whether it exists or not, whatever. It's just, it will be a variable to point to a integer node. So we've got this. This is, we see our two attributes here, and we've got our get sets. Well, let's do a constructor. A default constructor, this looks pretty good to me. I'm just going to go do it this way for easy copy paste. So let's go int node. There. The data is nothing, next is nothing. There, done. And for consistency, let's do this. And then here, the not default constructor. Well, I guess in this case, I'm giving the node an integer pointer that is to be the data, I guess. Cool. I mean, I could add more constructors if I want, but I'll keep it simple. Our copy constructor, again, this will be super simple. Now, you'll have to be careful though that this is not a very deep copy. The copied node, the pointers will be pointing to the same. I'm going to draw it in Paint again. I like using Paint. If I have like, what? Let's do this, okay. If I make a copy of a node, maybe this is head, it's going to make a new node, and say I'm copying this one here. If I make a copy, so this node has a pointer to its next node, and this node also has a pointer to its data. I don't know, the number 1. When I make a copy of this, it's copying over the pointers, not the values. So this will have a pointer to that same exact number 1, and its pointer to next will actually be a pointer to this one's actual next. So with this particular implementation, it is a not deep copy. Now, this one might throw you off a little bit too, because you might be expecting the deconstructor to have something in it, because we've got a whole bunch of pointers, right? Like data is going to be a pointer to an integer, and next is going to be a pointer to another int node. So you might say, well, hold on, they're going to be in dynamic memory. You might want to delete them. Well, here we won't do it because this node object is not going to be responsible for the creation and deletion, the allocation and deallocation of any of that RAM. Someone else is going to do it. Someone is going to make a new node. You'll see, like, I don't have next being equal to a new node anywhere in here. New node will be created somewhere else, maybe in like the main. And then I will tell an individual node to set its next to that new node that was created. But this node object here isn't the one responsible for that memory. It's just all this does is keep track of pointers and bookkeeping of data and where it's stored in RAM. That's all. Someone allocated that RAM, and they're going to be the ones responsible for deleting it, but not me, not the integer node. We'll see examples of this to clear this up. And some other stuff, I guess. We've got this. Oh, and do note that you will often see many implementations of these nodes not even have getters and setters. People will be lazy and just make these public, the attributes, and that's typical for nodes because it's such a simple class that, you know, maybe it's overkill doing the accessors, like the getters and setters. So yeah, they'll just make them public so they can attribute the data directly, like the attributes directly, but in this case, we'll do the getters and setters because we'll be good. So we've got our getters and setters, and that's it. That's it. That's literally it. So that's honestly it for now. Don't worry, we'll be putting them to good use very soon. For now, let's just do some testing. Okay. So if I were to write this code, I'm saying, okay, int node pointer head equals a new int node. So I'm creating a new integer node, and I'm giving it a new integer with the value 0, okay? And then n is head. And if I were to say n get data, what would we expect to see here? Well, n is pointing to head. So I've got head, and this points to the number 0. And then we have n, which is also pointing to head. If I say n get data and then dereference it, well, n's get data, dereference, well, that's just the number 0. Let me actually just throw this code into C++. I'm going to go to my main, and then here I'm going to have to include int node. Awesome. Do I need a semicolon after that? I can never remember. Do I have them? No, I do not. Okay. So in this case, let's just build this. And then I'll hit run, and I should see the number 0 printed out. And of course here I'm being bad. I'm not deleting anything after, but that's okay. So what do we see? Yep, 0. Okay, good. I'm not crazy. Good. So what does this next slide say? Well, for I is 1, so I'm starting at 1 here, not 0, because I already have 0. Yeah, I'm gonna run this code. And what do we think's happening here? So I'm saying n, you're next, and like n was pointing to head originally. And I'm saying n, your next is now a new integer node with the integer, with a pointer to an integer 1 in this case, and then n is being moved to its next. So after one iteration of this loop, n will be pointing to the node that's right after head that we just created, and yeah, that's it. And then the loop runs again, and then we add a new node. It's to be n's next, and it's going to be having the number 3. Or 2. Yeah, 2. And then n is now going to point to that node, and so on and so on and so on. So after I run this, what should I expect to see? Well, I'm going to draw this out. If I have, this is what I started with, head. Why does this keep happening? If I have head, and it points to here, and it's got the number 0 in it, okay? Actually, you know what? For ease, I'm just going to draw the number 0 inside it, but do note that it's actually a pointer to a number. And then I said n is that, okay. Then I have that loop, and what does the loop say? The loop says, okay, n, set your next to a new node, blah, 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 blah. So there's a lot going on here. And we usually work outside or inside out. So we create a new integer and then put that in the node and then set n's next to that. So ultimately what we've done is after that first line there, we've got, okay, a new node's created. It's got the number 1 in it. N, your next is now set to that. And N, you're now not pointing there anymore. You're going to point there. And then the loop's going to run again. It's going to create a new node, put the number 2 in it. N's next is going to be set to that new node. And then N's not pointing there anymore. It's pointing to its next, which we just set to be 2. And then again with 3. And then this gets, you know, and so on, all the way up to 9. Because we go less than 10. I could have made this 11 to make it 10, but whatever. And then, if I have this, what do we see? Well, what am I doing? Well, I set N back to head. And I'm saying, well, N is not a null pointer. Print out N's data. And then N, go to your next. So here, I'm just iterating over this linked structure. And this isn't counting at all. This is just looping until N is null. So this goes to that question Cole asked a moment ago about, what's the value of having the last node point to null? Well, we can use stuff like this to check the end. 0, and then here we see 0, 1, 2, 3, 4, 5, 7, 8, 9. Because if we go here, if this here is pointing to null, which remember, when we look at our default constructor here, for the node, by default, its next is null pointer. So it's null. So what I've done is I said, okay, N is first pointing here, then it points here, then it points here. And every time it moves down, it's asking, hey, are you null? No, okay, keep going. Da, 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 da. It's gonna get to 9 and be like, hey, are you null? No, okay, go to your next. And then it's go, hey, are you null? Yes. Oh, well, I'm done. I stop. Perfect. So there you go. We can use this while loop with this catch, with this condition of while you're not null, keep going to the next one. It's fantastic. And then here, if I want to delete everything like a good programmer, I'm going to want to do this. So what am I doing? Well, put N back at the beginning again. Well, N's not a null pointer. N is its next. Delete the head. Actually, delete the head's data, right? Then delete the head and then set head to N and so on. I guess I could have used a third variable here because head's kind of playing double duty. But yeah, there, I just iterated through and deleted everything. And then, of course, there's also these doubly linked structures where we could totally have a head and a tail. And each individual has access to both, has a pointer to both its predecessor, which in this case, it would be like null pointer because it's the beginning, and its successor. So if you ever want the previous, you could just say get previous. But I'm assuming you, I'm sure you can understand and appreciate how much more bookkeeping would be required for our inserts and deletes. There's a lot more pointers to keep track of. It's not prohibitively difficult, it's just a little bit more difficult. And we're not going to use these doubly linked structures because part of the exercise is using this limited, constrained, singly linked list and then seeing what we can do with it and playing around with it. So that's that for linked structures. And when we, so the next thing we're going to learn, not today obviously, is generics. And then we'll make a generic node. Basically with generics, we're going to be breaking a lot of the rules of thumb that we had already. And then what we're going to do after learning about generics, we're going to completely re-implement the stack, but with a linked structure, not an array. But with that, we'll wait until next Tuesday, I suppose. So yeah, have a wonderful weekend. And for those of you who have lab today, I'll see you in lab.